Okay, I see that more people are joining. And while we wait for the rest of the audience to connect, I would like to ask those of you that are there connected already, where are you from? Where are you connecting from? You should be able to write your country in the chat. And this is a way for us also to understand where our audience is located. Wow, I'll read Egypt. So really, really cool. The Netherlands, Slovakia, France, Finland, Switzerland, Belgium again. The Netherlands, Germany, Spain. Wow, there are really a lot of different countries. So super cool for us to know that geographically speaking, our audience is a bit everywhere. So I guess that we can move on to the next item on the agenda, which is actually to present the agenda. But first of all, welcome to this event. This event is called Heat and Eat, a matchmaking event for industrial heat pumps and the food industry. And my name is Sonia Bianconi. I'm EU Projects Manager at the European Heat Pump Association, and I'm joined by my colleague, which is sitting right next to me, Irene Geasaif, also EU Projects Manager at EHPA. So let's take a look at what we should be expecting from today's event. It's a 2-hour event. We will have 2 different sessions. The first one will have a more general and normal presentations mode, let's say. And we will have 3 different presentations by our experts, Eric Lecomte from the European Commission, DG ENER, Josh Gartland from the European Association of Sugar Manufacturers, and Rossen Ivanov from Armstrong International. In the second part of this event, we are going to move to a more interactive mode. So here we have the matchmaking session, whose rules Irene is going to present to you. And then we will have 1 hour of matchmaking session with 2 rounds, having 5 use cases per each, and we will have the prawn processing in Norway. We will hear about sugar production in Belgium, a use case from the brewery sector, and then also we will hear about some pineapple drying processes in Uganda and pelagic fish production in Norway. All these processes have been integrated with a heat pump, and you will be able to listen to these use cases and learn more about them. And finally, we will bring you back to this presentation mode, and I will close the event and tell you how you can get the material that we will be sharing today. So if we go to the next slide, I can introduce a bit the remote platform interactions. So in the first session, as you can see, you can only send reactions and type messages. There will be no Q&A for the presenters, so you will not be able to ask questions to our experts here. Please make sure that you save all your questions instead for the second session, where you will be able to switch on your camera and mic, send reactions, type messages in the chat. And of course, as I said, questions are very warmly encouraged. And before leaving the floor to our speakers, I would like to give you a short intro of the 3 projects that we have here today. So these projects are, this event is being organized in the framework of these 3 projects. They are research projects funded under the Horizon Europe program, and they all aim at fostering the uptake of high temperature heat pumps for industrial application. So we have Push to Heat, whose demonstration sites are located in the paper industries and in the chemical industries. Then we have SAS Heat, Spirit, whose demonstration sites are located in the in a sugar factory, in a prawn processing plant in Norway. And about these two demo sites, you will already be able to hear in the matchmaking part. And also a paper plant in Czechia is one of the other demo sites. And then we have Sassit, that aims to develop a new generation of highly efficient AI-assisted heat upgrade systems to harvest and store renewable energy for intensive factory processing needs. And also about this, a case study will be presented in the second part of this event. And without further ado, I think that we can stop sharing the slides and allow for our first speaker to start presenting, Eric Lecomte. While Eric, you share your presentation, I will say a little bit about you. So Eric Lecomte is Policy Officer at the European Commission, DG Energy, since 2015. And as Policy Officer at DG Energy, Eric is in charge of energy efficiency and transition to carbon neutrality in industry, but also heat pumps for industrial and commercial and residential applications and direct current technologies. So thanks a lot, Eric, for being here and presenting this and presenting EU funding opportunities in support to R&I and deployment of high temperature heat pumps. Please, the floor is yours.
Good morning. Thank you very much for the introduction. It's a pleasure for me to be with you today. Can you see my screen in full screen correctly?
Very well, yes.
Okay, all right. So indeed, I will talk about EU funding opportunities to support R&I, but also to support deployment, we will see. So beyond research innovation in Horizon Europe. So yeah, I'm in charge of the slides, I think. So yeah, so this is no surprise to you because you kindly already introduced the first three projects that are shown on the slide here. So indeed, we had the first call for demonstration, so in what we call an innovation action. So for technologies that are already well developed but need to be demonstrated in industrial environment, and there's a case for push to heat and spirit projects which started in 2022. Sorry. And then the following topic was also about heat pump, but here it's a research innovation action because it's about heat pumps for supplying even higher temperature in the range of 150 to 250 degrees Celsius. So already was presented to you briefly the project SUS Heat, but there is a second project in that under that same call, that is Tech Upgrade, which is also about developing heat pumps to recover and upgrade heat up to 150 to 250 degrees. Yeah, it will even be demonstrated into locations. Then also in 2022, there was a call for thermal storage at high temperature. It's not directly heat pumps, but usually heat pumps are coupled with thermal storage. So two projects there that are of interest to your community, Hercules and Heaternal, which started a bit later, so in 2023. So that's for the past. Still also projects that started. So the first one you see, integration of renewable heat and industrial waste heat in heat to cold. So it's here for the generation of cold, with also machines that can be considered as heat pumps, as they transfer heat from one source to the other. So a project that started in 2024. Next, you see electrified heat topic. That topic is about alternative heating systems for efficient, flexible, and electrified heat generation in industry. So it can be microwaves or other techniques to have a very flexible and focused heat generation in industry. The deadline was April this year, so we don't know yet which projects will be able to start. And then also about storage, geothermal reservoirs, there is the project Push Heat. And finally, geothermal heating and cooling. Not about heat pumps, maybe, but also relevant for your sector. Now, looking more into the future, and that's the work program 2025 in the Horizon Europe Cluster 5, the one of which I'm in charge of. So there we will have one topic, but the bulk of the topics will be in Cluster 4, obviously in the processes for planet partnership. So this is only a draft that can still change, of course. So it's about really phasing out fossil fuel in energy-intensive industries through the integration of renewable energy sources. And so indeed, phasing out in plants where there is a significant heat or cool demand, with a local integration of a combination of renewable energy sources, storage, process flexibility, but also heat upgrade by means of industrial heat pumps, and even combine heat and power from renewable biomass. So really a lot of freedom given to those projects to ultimately reach the complete phase out of fossil fuels. And interestingly, the needs of the EU factories, of all EU factories in the same subsector will be surveyed. So not only one factory, but the whole sector, to design a solution that can be adapted to most of those plants in the EU. So there will be physical demonstration, but to demonstrate this significant share of total energy demand by means of renewable sources, but also numerical simulations to demonstrate that this physical solution can be scaled up to produce nearly all the energy that is needed in the plant. Now let's go more to deployment. And this is a call not under Horizon Europe, but under the LIFE program. And it's about fostering collaboration, supporting collaboration between industrial sectors like paper, like food and drink, as is the case today. And on the other side, the community of industrial heat pump technology providers, really to optimize and integrate industrial heat pump solutions in industrial processes. So again, the objective is to move away from a custom-built project by project approach for a specific industrial plant and process, to a more streamlined, standardized set of solutions for an industrial sector and the processes in that sector. So not looking at one plant, but at a sector or the process, one process in a sector, but with looking at many industrial plants. And so it's about developing, disseminating knowledge and guidelines and business models eventually to foster the wide deployment of the solution in the sector. So the budget is 1.7 million. So it means it's not really about demonstrating a solution hardware, but really bringing two communities together, an industrial sector or subsector with similar needs in terms of process heat needed, and discuss with the community of heat pumps to design a solution that can meet the needs of most of them again. So actually, it's a bit to replicate the cooperation that took place between the paper industry and the Heat Pump Association. And actually, that's something that we support very much under the SET plan, the Strategic Energy Technology Plan, which is a cooperation between countries, industry, research institution, and the Commission to align research and innovation strategies. And we have several groups. You see in green there the renewables, energy systems, but also the energy use, energy efficiency in buildings and industry. And it's particularly this group, energy efficiency in industry, that is supporting the deployment of those technologies. And now I will continue with some slides borrowed from CEPI to explain a bit, yes, how they had this joint working group between the paper industry, CEPI, and the Heat Pump Association, EHPA. And this is something that we would like to replicate, for instance, in the food sector, hence very relevant for today in this workshop. So several steps that they have taken, 5 steps, which I will now describe a bit more in detail. So the first step is to make a survey of all the industrial plants, in this case paper, to define what is the virtual average paper mill. You see in gray all the heat needs, the 4 gray boxes, and on the left orange, the source of heat, of waste heat at the exhaust of the process. So describing the average paper based on the survey, that is the first step. The second step is to discuss with the Heat Pump Association to design a common heat integration design using heat pump. So you see the heat pump on the left that is using the exhaust air to produce steam, distribute the steam in the process, and then have you see at the bottom 3 consecutive recompression to produce, to raise, to upgrade the steam pressure and temperature to really meet all the needs in the paper mill. So that is the schematic of the solution. But then there was a discussion because actually the needs expressed by the paper industry were a bit difficult to achieve efficiently by heat pumps. And so they discussed what is the real pressure need, temperature need, and then they realized that actually they didn't need such high temperature or pressure, and so they reassessed the needs to optimize the heat pump solution. And so indeed, the last 2 steps were to agree on standard elements that you see in the orange brown boxes there, the heat pump compressor on the left and the vapor recompression stages on the right. Also on types of refrigerants, instrumentation and control, and also applicable codes and standard. So indeed, agreeing on common elements that would then be developed and standardized by the heat pump industry, and then standardization and certification. but still then keeping flexibility inside each paper mill to arrange those common elements in the way they want in each individual paper plant. So the benefits are indeed to have a common design, a standardized compressor, which much lower cost. Of course, better knowledge of each other, paper industry knowing heat pumps knowing paper sector, understanding each other, and definitely lowering the risk for individual paper plants to go into the deployment of industrial heat pumps. And with a lower risk and lower cost, of course, the business case is easier to build and easier to convince banks to go into the venture. So you have the link to the paper that describes this. And that's it from my side. Thank you very much.
Thanks a lot, Eric, for being first very on time and on schedule, and of course for the overview of the past ongoing projects and open calls that I'm sure someone from the audience will apply to in the next months. And also thanks for mentioning the collaboration between CEPI and EHPA. Indeed, we are working to replicate the same collaboration with the food and beverage sector, and we hope that this event will be one of the many to come in this framework.
Yeah. And maybe what I would say is that indeed the food and drink sector is a very varied sector. So probably subgroups identifying processes, because of course a brewery is not the same, has not the same needs in terms of heat as a pizza factory. I don't know what else. So really to come with homogeneous groups and define solutions that make sense. Thank you.
Certainly. Thanks a lot, Eric. And without further ado, I will introduce the next speaker of today, which is Josh Gartland from, indeed, the European Association of Sugar Manufacturers. So let's hear what the sugar industry has to say about this collaboration with the heat pump sector. While we wait for Josh to share the presentation, I will shortly introduce him. Josh Gartland is Deputy Director General of the European Association of Sugar Manufacturers, and previously he was Senior Advisor for Trade and Competitiveness at the European Wind Energy Association, Wind Europe. Today, he's going to present the EU Sugar Manufacturers Climate Neutrality Toolbox. We can see your presentation, Josh. Don't know if you want to put it in presentation mode. Otherwise, it's we can see it anyways. And the floor is yours.
Thanks, Sonia, and thanks to EHPA for organising this event. I think it's really interesting. Let me just go to full screen. So yeah, today I'm going to present a document we published last June, which is called the CEFS Climate Neutrality Toolbox. Perhaps first of all, who is CEFS? So CEFS is the Comité Européen des Fabricants de Sucre, or the European Association.
Josh? Yeah. Can I just interrupt you because we cannot see the screen in full presentation mode, and we cannot see the slides changing. So
okay. Maybe I can share my screen instead of my window. Let me see.
Probably. Otherwise, we can try and share it for you, but let's give it a try.
Okay. So how does that look?
Better. Perfect.
Yep.
That's great.
Okay.
Thank you.
Okay, so perhaps a quick introduction to CEFS. CEFS is the European Association of Sugar Manufacturers. We have a French acronym that means the same thing. And we represent sugar producing companies in the EU and Switzerland. So we basically buy the sugar beets which is an agricultural raw material that we cultivate here in Europe, and we process that into white sugar, but also other products such as molasses, animal feed, bioethanol, biomethane. So we're, I think, a very good example of a circular economy, bioeconomy sector. We have 88 beet sugar factories in the EU, and also 2 in Switzerland. So here you can see the distribution of those production sites. And in June 2023, we asked ourselves what tools are available to decarbonize our sector and what policies are needed to get there. We're quite a specific industry. You can see a pile of sugar beets there in the bottom left. So we process around 100 million tons of them every year to produce roughly 15 million tons of sugar. And to produce that sugar, we use large volumes of heat and, to a lesser extent, electricity. So we are an energy intensive industry. We're on the ETS carbon leakage list, so we get free allowances. But perhaps more specifically than, for example, the paper industry, we're a seasonal industry. We rely on the harvest of the sugar beets, and because sugar beets are perishable, we have to process all of those sugar beets within 3 to 4 months. So that means any investments we make will only be in use for perhaps a third of the year. And that obviously has implications for the amortization of the investments, and also for the size of the installations. Our cogeneration units have to be 3 times as big as if we were operating year round. Again, because we have to produce everything within this seasonal time period. Another specificity is that our factories have to be located close to the sugar beet fields, and that's because again, sugar production is quite transport intensive. It takes around 7 tons of sugar beet to produce 1 ton of sugar. So to minimize those costs, it's better to have the factories located close to the fields. Because of that, many of our factories are located in rural areas, so they don't often have access to high voltage electricity grids, and that has implications for electrification. So I think it's really important to take into account the specificities of our industry. Here's a diagram of sugar production. So you can see the various stages. We use heat in a number of phases. We use heat to dry the beet pulp if we're producing dried animal feed. That's not always the case. We also use heat in the lime kiln to produce quicklime, which we use in the purification process. But the main phase in which we use heat is the evaporation stage, and this is where we're basically evaporating the water from the sugar beets, which are 70% water, in order to get a very high concentration sugar juice. And then we centrifuge that, we spin it around in order to extract the solid sugar crystals. So we have made progress in reducing our CO2 emissions. You can see since 2017, there's been quite a good reduction, both in absolute terms and in terms of kilograms of CO2 per ton of beet processed. So we do produce less sugar than in 2017 due to various reasons, but emissions are down not just because of that, and they're also down for every ton of beet we process. And if we take a longer term view, we can see that emissions are down 59% between 1990 and 2021. So we've already reached the Fit for 55 target. We think that we'll deliver another 30% reduction by 2030. And we're aiming for climate neutrality by 2050 in line with the EU. So this is a possible trajectory of emissions in the sector. And of course, there's an economic imperative to decarbonize. We're a carbon leakage sector again, and therefore we will see a reduction in free allowances at a higher rate than previously, and also emissions allowance prices will increase. In terms of the emissions hotspots, I think the biggest one is the production of heat and electricity. Our factories, because they're located in rural areas, they generally produce heat and electricity on site. I mean, all of them actually produce heat and electricity on site. And that can be over 50% of energy usage, generally more, and over 60% of emissions. Where the beet pulp, which is the kind of the fibrous non-sugar residue, where that is dried to produce animal feed, that can use up to 50% of the energy generated, and it can contribute up to 30% of emissions. And then we have the lime kiln, which can be 5% of energy and up to 10% of emissions. It's more emissions intensive because we generally use coke as the fuel in the lime kilns. There's no single sugar beet sugar factory configuration, and there's no single solution. So here you can see some factories produce dried pulp for animal feed. Some factories produce bioethanol. Some factories produce biogas. So you can see there's different configurations and different products which are produced, different decarbonization solutions. We identified a number of tools. We split them into two baskets. So the first one was renewable energy, which can be own biomass residues. It can be external biomass and biomethane, and it can be on-site renewables. And then we identified other tools such as low temperature drying of beet pulp, for example, where you would you reuse the waste heat from the sugar production process to dry the beet pulp. Heat recovery, such as, for example, additional evaporation effects, where you reuse waste steam in order to increase the efficiency of the evaporation stage. Heat pumps, which could be industrial heat pumps, but could also be mechanical vapor recompression, which we already use in the industry. Lime kiln conversion, which is where we would switch from coke to a less emitting fuel, or potentially even purchase the limestone that we use externally. And then another tool which is not used as yet in the sector, which is carbon capture. Own biomass residues will be essential, especially in the short to medium term. So that's mainly the beet pulp. We think that could generate sufficient energy to power the factory, especially if it's a very energy efficient factory. Heat recovery and electrification will play an important role. And here you can see the evaporation effects in a sugar factory. So the more of them, the more efficient the factory and the lower your emissions. The ceiling is perhaps 9. You could probably have about 9 evaporation effects before it's not really worth adding anymore. That being said, in many cases, efficiency improvements are reaching their limit. For example, here you can see Germany. The energy use in the sugar industry has plateaued since 2020. So perhaps we need to look into other solutions. One of these solutions is high temperature heat pumps, but these are still in testing phase, and the consensus among our members is that electricity prices need to be brought down in order for these to be viable. If the coefficient of the coefficient of performance of your heat pump is 4, for example, but the electricity prices are over 4 times as high as your natural gas prices or your cost of production of biomethane, then the industrial heat pump is not going to be viable. So lower electricity prices are really essential in order to make this solution work. There's another type of heat pump that I mentioned, which is called mechanical vapor recompression. You're basically recompressing the steam mechanically in order to increase the temperature. But then that's generally compared with another solution, which is thermal vapor recompression. And thermal vapor recompression is generally preferred just because it has lower capital expenditure, and because it requires, again, lower electricity prices to be viable. Other important things for installing mechanical vapor recompression are the heat schema in the factory and the level of grid connectedness. Again, a general issue for us is that our factories are located in rural areas and don't always have good connections to electricity grids. Our members, sugar manufacturers, already use on-site renewables. So this is Iscal's factory in Fontenoy. So these are already playing a supporting role, but again, they don't provide the constant volumes of electricity we need, and they don't produce heat. Here you can see some solar park in the Netherlands, and here actually on the right, that's Iscal Fontenoy in Belgium. So the consensus is that full electrification is not for tomorrow, and something we hear, I think, far too much about is renewable low carbon hydrogen. I think it's going to be very expensive and scarce, and is not an appropriate solution for the sugar industry. So in terms of the policy framework, we're asking for a pragmatic implementation of the Renewable Energy Directive to allow us to use biomass residues, Energy Taxation Directive, if that ever comes to light, we would want that to exempt the energetic self-use of residues. In general, electricity prices should be brought down. If the EU wants us to electrify, make it cost effective to do so. And then the final request is we need direct financial support, grants, loans, carbon contracts for difference. So support that targets both the CapEx and the OpEx sides. That concludes my presentation. Thanks a lot for your attention and for the invitation.
Thanks a lot, Josh. Thank you for telling us more about the EU sugar processes, and of course the specificities of this industry need to be taken into account in order to integrate CO2 reduction technologies such as heat pumps, for example. And I was actually very impressed with the numbers, to see the numbers that you showed in terms of emissions reductions that you've achieved so far. So great job, I would say. And let's now move to our next speaker of today. Last but not least, we have a representative of the heat pump industry, Rossen Ivanov from Armstrong International. So let me tell you a bit about Rossen. He has graduated from the MBA Solvay Brussels Schools of Management and has been working with Armstrong International since 1996. And currently is also managing director of the European, Middle East and Africa division since 2013, as well as member of the Global Executive Council. I see that you have already shared your screen. I can see it perfectly, Rossen, so please, the floor is yours.
Thank you. Can you hear me well?
Very well.
Thank you. So yeah, just in a nutshell, Armstrong, we're a 125-year-old privately owned company, present globally with more than 3,000 employees. And we're coming from the utility side. The steam and condensate system historically used in the food industry and many other industries such as refining, petrochemical, chemical, pharmaceutical, etc. Interestingly, our journey has brought us toward energy efficiency, looking at the steam and condensate system, but also recognizing that steam is not the most efficient way to heat below 100 degrees. It's actually a bit challenging to use steam under vacuum. So we went into de-steaming and hot water use as a heating media. And then we crossed the mirror. We went on the other side of the process and found waste heat recovery as a potential for further energy efficiency. First, direct heat recovery using high-grade heat, and then lately low-grade heat recovery using heat pumps. The reason is decarbonization. That's the paradigm shift for all of us, end users asking for ways to decarbonize completely their plants. And we reached the conclusion that the only way to decarbonize heat without increasing significantly the energy cost is to leverage the significant amount of free decarbonized local waste heat available at the plants. So we put together a design methodology called circular thermal, where we are bundling pinch methodology, direct heat recovery, and low-grade heat recovery, using also de-steaming as a way to facilitate the implementation. As we did not have the technology in-house, we partnered with a German company called Compiterm, which have been manufacturing heat pumps for 50 years in Stuttgart, including above 80 degrees for the last 20 years. And we are currently scaling up manufacturing of this technology across the globe, US, Belgium, India, China, and Mexico. The principle of circular thermal is quite simple. I hope the video is going to run well. Historically, since the Industrial Revolution, we have been using one-way system. So we are putting energy on one side of the plant, typical natural gas, which is burned in boilers. Part of this energy is lost in the boiler house or in the distribution, condensate return, flash steam network. Only about 80% of the primary energy ends up in the process, and very low quantity of that energy goes in the product. Some products are, other products require chemicals, but most of the time, energy is wasted in the form of low-grade heat through process stacks. The idea here is to apply the circularity to heat, where we apply circularity to material and we apply circularity to water. This would mean recovering the high temperature, the low temperature stacks and upgrading it to high temperature using heat pumps, as it has been shown so far. And the electrification allows also to decarbonize if renewable electricity is being used. The impact is a significant reduction of primary energy, up to 80% in the food industry, which typically require temperature below 200 degrees centigrade, and often less than 100 degrees centigrade. A practical example, and there will be a lot about Norway and fish today. This is an aquafeed plant from Cargill in Norway, a dryer implemented by a Dutch company called Galen Counterflow with heat pumps from our partner Combiterm. The principle is the same, condensing the stack in order to get the latent heat. That's where the most energy is, using water network as a source, and then creating superheated water as a sink in order to heat the air. 75% reduction of the primary energy and 3,000 tons of CO2 per year. The trick there with the improvement of the COP is to use different temperature level within the dryer in order to minimize the lift at every stage. The case is described in details in the International Energy Agency Annex 58 Heat Pump Technology Center. This is the plant room with the dryers for a total of 3.5 megawatt thermal, 4 heat pumps, and 10 compressors overall. I'll skip the video for the sake of time. It's on YouTube, and you can have a look at it. It is showing the factory and the dryer with implementation. What's interesting is to look at the sites beyond geo applications, where it's relatively straightforward to apply the circularity of heat because source and sinks are correlated. Things start to be a bit more complex when we look at complete factories. The first point is that cooling systems are significant sources of waste heat. Cooling is about taking heat out, and chillers typically have a COP of 3, so they would produce 3 times more waste heat than their electrical consumption. So plants using refrigerant system going into deep cooling, such as frozen meat or ice cream, there would be significant sources of waste heat. Eliminating cooling tower also helps with the water targets of our customers, because cooling towers are one of the most significant users of water within industrial plants. On the heating side, as already mentioned, the stacks can be recovered. We're looking at de-steaming because generating with heat pumps is feasible, but it requires quite a lot of capex and opex. So lowering the bar for heat pumps would be to move into superheated water below 120 degrees C. The other advantage is that we can store water relatively easily, while storing steam is quite impossible. They are steam accumulators, but practically they are superheated water tanks, and then steam is flashed. Direct heat recovery always comes before heat pumps, and this is shown through the pinch methodology. The pinch methodology has been around for more than 40-50 years. This is how very energy-intensive industries such as refining chemical plants are designed. The goal there is, instead of having in parallel energy use for cooling and energy use for heating, these streams are overlapped, and the gray zone shows the area where temperatures are overlapping, so it is possible to implement direct heat recovery using just heat exchanger to recover high-grade heat in order to preheat something at a lower temperature. This is going to minimize the quantity of energy needed for cooling and heating. However, this energy is still required. Using heat pumps, doing this difficult work of recovering low-grade waste heat at the lowest temperature and bringing it up to the highest temperature needed in the plant is allowing to further decrease the overall primary energy. In the curve on the right, the only energy going in the plant is actually the electricity for the compressor in the heat pumps. And we're reaching that kind of design leveraging pinch methodology in quite a lot of food plants requiring low temperature. The other point in the pinch methodology is looking further and further in the temperature needs. Many people start by asking heat pump at 170 degrees because that's the temperature of steam they're currently using in their utility system. That's what we call the black box in the pinch methodology. Going beyond the control valve, looking what's going on inside of the heat exchanger is quite interesting. Often control valves are decreasing the temperature of steam quite significantly. In that example, 130 degrees. Going even further and looking at the other side of the heat exchanger, at the actual process temperature, is often very eye-opening. and it allows to further maximize the coefficient of performance by minimizing the temperature lift. And this is the white box in pinch. And amazingly, the process engineer today starts to be very open-minded once the consequences of these high temperature lifts are understood. Minimizing the temperature lift really allows to decrease both the capex and the opex on the heat recovery side. Of course, the heat exchangers need to be bigger. We need more heat exchange surface with hot water than we need with steam, and that's the kind of trade-off which is designed every day. As mentioned, heat pumps can generate steam at low pressure, and this steam can be further compressed using MVR. MVRs on the market and steam compressors of various technology allows to reach 200 degrees centigrade. Going further might be technically achievable, but the lift starts to be important. The sources within food plants are again cooling systems, the energy, the waste heat going to cooling towers, and the other source are the stacks, and condensing these stacks often result into less than 100 degrees. So lifting that temperature by more than 100, 150 C would become uneconomic, even if it is technically feasible. The second important point to understand is that steam systems are not just one way. Condensate needs to be recovered beyond the heat exchangers. These systems should be as close as possible, so flash steam should be recovered and condensate should be recovered in order to be sent back to the evaporator. An example of a steam in our demo unit. How do we optimize the efficiency and the cost of this circular thermal system? The temperature lift is a very important criteria, but beyond that, this steaming helps. We eliminate the boiler houses, but helping also eliminating the flash steam losses brings further cost saving. And then the integration of the heat pump with the system is a very interesting area of development. Heat pumps are not that simple to design. They can be quite flexible in the refrigerant loop. We can integrate quite a lot of heat recovery within the heat pump. And on the other side, the system can be adapted so that it can maximize the efficiency of the heat pump. And this efficiency integration, thermal integration, brings a lot of improvement in terms of COP for the system. Finally, in terms of cost, heat pumps typically come with hot water tanks. Some people call them thermal batteries now. They help store heat, and this system can run when a spot price of electricity is the lowest. So they help the grid, they help with the intermittency of renewable, and they help also lowering the cost of the system through the year. So a typical roadmap in the food industry might look like this. Steaming helps lowering the bar for waste heat recovery. Direct heat recovery should be used first, and then low-grade heat recovery with heat pumps. Only then come the switch to renewable, the biomass, the biogas, potentially carbon capture, or the e-boilers. They might help fulfill the gap which remains in terms of energy efficiency and in terms of CO2 emissions. But these should not be used before waste heat recovery. The risk is that we start using renewable and start generating renewable waste heat. And that's the last thing we want to do, considering the investment for renewable energy. So for those who are interested, we have a white paper on the subject of circular thermal, and it develops further the concept. That's it for me.
Thanks a lot, Rossen, also for being perfectly on time. Yeah, thanks for giving us this overview of the various technologies that can be applied to the various food sectors. And yeah, thanks to you, and thanks to all our speakers.